Hello everyone. The title of this video is Identifying Horizontal Asymptotes and Slant Asymptotes of Rational Functions. So every example I'm going to be doing in this video is taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 5.6, called Rational Functions, and I'm under the heading Identifying Horizontal Asymptotes of Rational Functions. Each example I'm going to do is either going to be an example directly from the reading, or one of those try it problems from the reading, or one of the exercises at the end of the section that's related to this particular objective. Okay, so I have some examples written out, but before I actually go into them, I want to talk about, real quick here, with that, in my own way this time, horizontal asymptotes and slant asymptotes. Really what we're talking about here is the end behavior of a rational function. Alright, now hopefully you recall from a previous video what a rational function looks like. It's any function that can take the following form. F of x equals, say, p of x over q of x, and I'm just writing it the way they have it in the text, where obviously the denominator is not 0. And this p of x and q of x, this numerator and denominator, are polynomials. Right, so it's a rational function is just anything that can be expressed as a ratio, a fraction, with two polynomials. Alright, so I'll tell you right now what the end behavior is going to be like for any rational function. As the value of x goes to infinity or negative infinity, alright, so the right end or the left end, f of x will approach the value of the quotient when dividing p of x by q of x. So the key is the quotient here. So basically, you have to remember how to divide polynomials, right? Which was discussed in previous videos earlier in this chapter in this particular text. Right, so if you know the quotient, remember there's a quotient and a remainder. If you know the quotient when you divide p of x by q of x, these two polynomials, you'll know the end behavior for your rational function, what happens on the right end and left end as x goes to infinity and negative infinity. Alright, so here are the cases. 1. If the degree of the denominator is bigger, so the degree of the denominator is greater than the degree of the numerator. If that's the case, well then you don't have an improper fraction, you can't really perform division. Right? Polynomial division was when you had an improper fraction, when the numerator had a degree that was at least as big as the degree of the denominator. So in this case, the quotient is 0. Right? If you're not doing division, if it's not an improper fraction, then the denominator doesn't go into the numerator at all. So the quotient is 0. So in this case, y equals 0 will be a horizontal asymptote. And we'll see examples of this, of course. The graph will basically be approaching the x-axis as you go to the far right or far left, right, on the ends. All right, the next case is if the degree of the denominator is the same as the degree of the numerator. All right, so if they have an equal degree, now if they have an equal degree, then you have an improper fraction and you can perform polynomial division, long division. And the quotient won't just be 0. Well, if they're equal, if they have the same degree, the quotient, right, won't just be 0. It'll just be the ratio of the leading coefficients. You'll see. Right, again, we'll do some examples. But just the ratio of the leading coefficients, which is going to be a number, no variables. And whatever this is, will be the horizontal asymptote for your function. And again, we'll see examples. Now, if the degree of the numerator is greater, then you'll have to perform long division. I mean, you have to perform long division anyway, but it'll be more steps if the degree of the numerator is bigger. Right. So the third case, if the degree of the denominator is smaller, is less than the degree of the numerator. Then y equals, again, the quotient, as I was saying earlier. Y equals the quotient, whatever that is, will dictate end behavior. The graph will approach the graph of the quotient function. Will dictate end behavior. And if this quotient is a degree 1 polynomial, if this quotient is a degree 1 polynomial, a linear polynomial, degree 1, then they would call this a slant asymptote. Right, so I had the words slant asymptote earlier. All right, if it's anything higher than a degree 1, then they might call it an oblique asymptote, but usually just call it whatever degree it is. But if it's a degree 1 polynomial, y equals 2x plus 1, 3x minus 5, whatever, They call that a slant asymptote. Again, or an oblique asymptote in some books I've seen. Alright, yeah, and that's it. That's really it. So what we're going to be doing here is a lot of division. And I'll keep going over to that free online graphing calculator at desmos.com and showing you the graphs and showing you what asymptotes would look like and all that. Alright, so let's go to this example here where we're given a rational function, polynomial divided by polynomial. We're asked to identify the horizontal or slant asymptote if it has any, for the graph of the rational function. So notice that they have the same degree, right? This is a degree 3 polynomial in the numerator, degree 3 polynomial in the denominator, right? So same degree. And remember what I wrote earlier, if they have the same degree, then you're just going to be looking at the ratio of the leading coefficients. That's going to be where the horizontal asymptote will occur. Well, the leading coefficients are 6 and 2, so 6 over 2 is 3. Y equals 3 will be the horizontal asymptote. Y equals 6 divided by 2. Again, this is just the ratio of the lead coefficients. Y equals 3 will be the horizontal asymptote for this function. And that's it. And it's very easy when the degrees are the same, or when the degree of the denominator is bigger than the degree of the numerator, right? You don't have to divide. Now, if you wanted to divide them, right, or you could actually perform long division, and you would see that the quotient is 3, right? Y equals the quotient is what the graph's going to approach on the ends. But just to refresh your memory here, right, the denominator is the divisor. What you're dividing into, the numerator, is the dividend. That goes inside, right? 6x cubed plus 0x squared minus 10x to the first, and then plus nothing. But then you have the divisor is 2x cubed plus 5x squared out here. And remember the steps for this. And I'm assuming you know how to do long division. I've done it in a previous video earlier in this chapter. Divide the lead term. 6x cubed divided by 2x cubed is 3. Then we multiply, that'd be 6x cubed and then plus 15x, and then subtract that entire line from the line above it, and you get nothing, nothing, and then negative 25x to the first. And once the degree after subtraction is less than the degree of the divisor, you're done, right? This is a degree 1 polynomial here. This is a degree 3, so we're finished. So we could say that g of x is, remember how to write a fraction, a division problem? Dividend divided by divisor is quotient 3 plus remainder over divisor. So minus 25x over 2x cubed plus 5x squared. And then look at what happens, as x approaches infinity or negative infinity even, this expression here will approach 0 because the denominator is so much bigger, it has a bigger degree than the numerator. And then the whole thing will approach 3 then, right? G of x would approach 3 minus 0. Again, just the quotient. What happens on the ends of these rational functions, the right end, the left end, the graph will approach the graph of the quotient when you do division, y equals 3. Well, let's see. Alright, I'm going to go to that Desmos website, and we'll see that y equals 3. is a horizontal asymptote, right? Well, the graph will approach that line on the right end and left end. So Desmos.com, free online graphing calculator. I'm going to enter the function as we were given it, right? G of x equals, the numerator has 6x cubed minus 10x, and then the denominator 2x cubed plus 5x squared. And I'm just going to put in the line, the horizontal line, y equals quotient, y equals 3. And I'll make it like a dashed line or something. All right, let's make this a dashed line. Okay, now again, all that this horizontal asymptote, slant asymptote, y equals quotient asymptote stuff is talking about is the end behavior. Do you see if I zoom out here, as you go to the far right, see how the graph is approaching y equals 3. It's approaching that dashed line as x goes to infinity. All right, same thing to the left end. All right, as you approach negative infinity, see how the red graph is approaching the blue dotted line. Right? The graph is approaching, getting closer and closer to y equals 3 without actually touching it, though it doesn't look like. Now it can touch, but it can fluctuate around as long as it's getting closer and closer to it. Then you have a horizontal asymptote. All right, so it looks like what I said was correct. Y equals 3. Right, the ratio of those lead coefficients is, when the degrees are the same, like here they were both degree 3, the numerator and denominator, that's the horizontal asymptote for this function. Right, and it really is that simple. If the degrees are the same, it's just, what's going to happen on the ends, the graph will approach y equals the ratio of the lead coefficients. That's it. All right, so next example. All right, so this time I have, the degree of the numerator is 2. The degree of the denominator is 1. All right, so here, the degree of the numerator is larger, meaning I have to divide. Okay, that was that third scenario I wrote out earlier, right? If the degree of the numerator is larger, then you have to do the division. You have to find the quotient. And the graph of that quotient is what the graph of the original function will approach on the ends. All right, so same setup. Now, since this is a linear coefficient with a lead coefficient of 1, you could use synthetic division, but I'm just going to do the long division again. So let's actually divide x squared minus 4x plus 1 divided by x plus 2. Right, the lead term in the quotient would be x. Then we multiply, that'd be x squared plus 2x. Then subtract. You got x squared minus x squared is nothing, then negative 6x. And then still the plus 1 here, and then divide the lead terms here. You got negative 6 is the next term in the quotient. Multiply, you got negative 6x minus 12. Subtract all that. 1 minus negative 12 would be 13. Alright, so this function, h of x, I could rewrite as x minus 6 plus 13 over x plus 2. Then again, what happens as x goes to infinity or negative infinity, this remainder term here, 13 over x plus 2, would get really tiny. So you'd be really close to just x minus 6. So y equals x minus 6 and is the graph that this thing will approach on the ends. And since this is a linear function, y equals x minus 6, they call this a slant asymptote. Is the slant asymptote for this function. And once again, I'll draw this out. All right, we'll look at the graph of h, and we'll look at the graph of y equals the quotient, y equals x minus 6 here, and see that the graph of h approaches that on the ends. so the function we were given, h of x equals numerator x squared minus 4x plus 1, denominator x plus 2. And you see how when I zoom out here, the graph's not approaching some horizontal line. See, the further and further I zoom out, it looks like the graph is like basically a straight line. See how the graph is basically a straight line as you go out further and further away from the to the right and to the left. Well, let me put in the graph of that y equals quotient. Y equals the quotient, y equals x minus 6, and I'll make that a dotted line or a dashed line. And you can see as you move to the right, the graph is approaching this dashed line, right? It's not actually touching it, it's always a little off, but it is approaching that purple dotted line, right? That's off to the right, and the same thing off to the left. If I go off to the left, same thing, right? It's just from below, right? The green graph is approaching the purple dotted line. Y equals that quotient. Okay. So it looks like we have a good, slant asymptote based on that picture. And this is all we're doing for the examples in this video. Alright, so I've had an example where the numerator and denominator had the same degree. The denominator had a smaller degree, and now here's that first case where the denominator has the larger degree. Well, in that case, the quotient is 0. You really can't perform long division. Right? Remember, long division stops when the degree after subtraction is less than the degree of the divisor. Well, the degree of the numerator is less than the degree of the divisor, so you can't even start the long division. The quotient is 0. So if that's the case, y equals 0, right? The x-axis is a horizontal asymptote. And again, I'll go to the Desmos site. We'll take a look at this and see that the graph of this function k does approach the x-axis to the far right and far left. Asymptote. Right. And let's see. Right, so again, back to that Desmos site. Alright, the function as we were given it, k of x equals, numerator has x squared plus 4x. The denominator has x cubed minus 8. Right. And I'll put in the x-axis, y equals 0. And I'll make it like a dashed line again, right? That is not actually part of the graph. And then you can see, as you move to the far right, the graph approaches that red dashed line. It doesn't actually become it. Right? You see, it's always just a little off, but it gets closer and closer to it. Same thing to the far left, right? You go to the far left, the graph is, approaching that red dotted line. It's approaching the x-axis. Not actually becoming it, but approaching it. So, the x-axis, y equals 0, is a valid horizontal asymptote here. Great. Alright, so when the denominator has a larger degree, it's easy, y equals 0. When they have the same degree, it's easy, just y equals the ratio of the lead coefficients, like in the first example. The only time you really have to do much of anything with the long division is when the degree of the numerator is bigger, like in example 2. Alright, so next one. Now this one's a little trickier because you actually have to do some multiplying out, but it shouldn't be that much harder. I mean, you know how to multiply polynomials, I hope. Here the polynomials aren't in general form, right? They're factored. But if you were to multiply them, 2x minus 1 times 2x plus 1 would be 4x squared minus 1. Right? And then x minus 2 times x plus 3 would be x squared plus x minus 6. So what I'm seeing here is that these have the same degree. They're both degree 2. And if they have the same degree, then y equals, just the ratio of their lead coefficients, so just 4 over 1. Y equals 4 is going to be the horizontal asymptote for this function. Right? The graph will approach the line y equals 4 as you go to the far right and far left as x goes to infinity or negative infinity. And let's see that happen. I'm going to show you most. I'll show you most of these. I don't know if I'm going to show you every single one, but again, I'll write the function as we were given it. We had 2x minus 1 times 2x plus 1 all divided by, and then denominator had factors of x minus 2 and x plus 3. And then I'll put in the y equals 4, right? What we said the horizontal asymptote is going to be that green line there. I'll make it a dashed line. And you can see, sure the graph is the graph hits the dashed line here, but that's not what we're talking about. We're talking about end behavior. What happens to the far right, the far left, as x goes to infinity, negative infinity. And you see, as I go out to the right, the blue graph gets closer to the green dotted line. And the same thing happens to the left. As I go out to the left, as x goes to negative infinity, the graph of our function gets closer to the green dotted line. Doesn't actually become it, but it approaches it. And that's all that matters. That's all we're saying. Okay. Next example. All right, so this one's another simple one, I feel. F of x equals 4 over x minus 1. This is the case where the degree of the denominator is larger than the degree of the numerator. So y equals 0 is going to be the horizontal asymptote here. And that's it. Right? And I'll leave the graph and verifying that that the x-axis is a horizontal asymptote. I'll leave that to you. So that one was pretty simple. All right, example 6. So I have a degree 2 in the numerator and a degree 1 in the denominator. So gotta divide. Right, so you can do the law division. Right, we're taking 24x squared plus 6x and dividing by 2x plus 1. The lead term in the quotient would be 12x. And then multiply that by the divisor. You got 24x squared plus 12x. And then we subtract all this from the line above it. 6x minus 12x would be negative 6x. And then, the degree is not smaller yet, so I keep going. Negative 6x divided by 2x would be negative 3. And then I'm done. Right? Then we'd have negative 6x minus 3, subtract all this, and the remainder would be positive 3. But here's the quotient right here. That's all that matters. Y equals 12x minus 3. And that's another linear function. This would be called a slant asymptote. Right? So this would be the slant asymptote for our function f. Right, so the graph of f is going to get closer, approach the graph of this line on the far right and far left. And let's see that happen, right? With the slant asymptotes, since most people aren't as familiar with them, we'll show those here. Right? We'll go to the Desmos site. So the function we were given, f of x equals 24x squared plus 6x in the numerator divided by, and then 2x plus 1 in the denominator. And again, you see if I zoom out a lot, it looks like the graph is going in a line to the right and left, from lower left to upper right. Got this line it's approaching. And the line it's approaching should be y equals the quotient, y equals 12x minus 1, or sorry, minus 3. And let me dash that in. And you should be able to see that, let me zoom in a little closer here, that if I go to the far right, see how the purple graph is approaching that black dashed line. And closer to it. And then as I go left, again the purple graph is approaching the black dashed line. Right? So that asymptote of mine, y equals 12x minus 3, looks pretty good. Looks like I'm correct in saying that that is the slant asymptote for this function. Alright, and my 7th example, another pretty simple one, which I'll leave to you to check. You can go to the Desmos site or graph it yourself. F of x equals x minus 4 divided by x minus 6. They're both the same degree. Right? So once again we have that case where they're the same degree. So y equals just the ratio of the lead coefficients, which is just 1 over 1. Y equals 1. And that's a horizontal line, right? So this is going to be the horizontal asymptote for this function. Very simple stuff, especially when they have the same degree. And again, I'll leave it to you. Graph this, take a look at the graph of y equals 1, and you'll see that the graph of f approaches y equals 1 to the far right and the far left, right, on the ends. All right. And then my final example. Degree 2 divided by a degree 1, so I have to divide. Now you can use synthetic division here. Right? Dividing by a linear divisor with a lead coefficient of 1. Since this is x minus 1, I'll put 1 here, and the coefficients of the dividend up top. Drop the 1. 1 times 1 is 1, plus 5 is 6. 1 times 6 is 6, plus 4 is 10. So the quotient is x plus 6. Alright, this is the quotient. So y equals x plus 6, and this is another linear function, degree 1. So this is again called a slant asymptote for this function. Alright, and one more time I'll show you that y equals x plus 6 is the graph that our graph of f will be approaching on the far right and far left, right? Alright, so the function we're given, f of x equals x squared plus 5x plus 4 divided by x minus 1. And again, if you zoom out, you'll see that it's kind of looking like a straight line. It's following a straight line path to the left and to the right. But let me actually put in that, y equals the quotient, y equals x plus 6, and we'll see that, the graph follows this line, approaches this line to the far right and the far left. So yeah, see if I go out to the far right, the red graph is approaching that blue dotted line, right? And the same thing goes is if I go left forever too. If x approaches negative infinity, the left end behavior, same thing, that red graph is approaching that blue dotted line, our y equals quotient. So yeah, looks good. Again, very simple, I feel. If you're given a rational function, polynomial over polynomial, divide them and see what the quotient is. That will dictate the end behavior. If the degree of the denominator is bigger, then y equals 0 is your horizontal asymptote, the x-axis. If the degrees are the same, it's going to be the horizontal asymptote will be y equals the ratio of the lead coefficients. And if the degree of the numerator is bigger, you have to divide. Now you can do long division all the time. There are only certain scenarios where you can do synthetic division. I would just suggest doing long division every time and find the quotient, and then the graph will approach the graph of y equals the quotient on the ends. Great, and I'm hoping that watching me go over these 8 examples here help you in some way when you're trying to do this stuff, identify horizontal asymptotes and slant asymptotes for rational functions on your own. And thank you very much for watching.